we can use the QR factorization to solve a matrix vector equation AX equals B in the case when A is square and its columns are linearly independent. In this case, A is an invertible matrix. So we know there exists exactly one solution because we can write it as A inverse times B. And here's the algorithm that we can use in this case. First, we find a QR factorization, a pair of matrices Q and R, such that A equals the product of Q and R. Q is column orthogonal and R is triangular. Next, we compute the vector C by multiplying Q transpose times B. And finally, we solve Rx equals C. And we can do that since R is a triangular matrix. So we can use backward substitution. And then return the solution to that. Why is that the correct solution? Let x hat be the vector returned by this algorithm. Now, because we solved this equation, we have that R times x hat equals Q transpose times B. Let's take this equation, multiply both sides by Q. So we get Q times R times x hat equals Q times Q transpose times B. Now, we can rewrite this using associativity of matrix multiplication. So Q times R times x hat equals Q times Q transpose times B. Now, QR is equal to A. So we have A times x hat equals Q times Q transpose times B. But Q and Q transpose are inverses of each other. So Q times Q transpose is the identity matrix. So we get AX hat equals the identity matrix times B. In other words, A times x hat is B. And we've solved the system. We've seen how to solve a matrix vector equation AX equals B, where A is square and its columns are linearly independent. What if the columns are not linearly independent? Here's an example. Let's say the matrix A consisted of the columns V1, V2, V3, V4, and these were linearly dependent vectors. Well, then there's a basis consisting of a subset of these. Let's say a basis consisting of V1, V2, and V4. We're trying to find a vector A times X that's equal to B. We're trying to find a vector of this form. But the set of all vectors of this form, A times X, is the same as the set where we omit the vector V3, because V1, V2, and V4 span the same space as V1, V2, V3, and V4. So if we want to solve a matrix vector equation, but the columns don't happen to be linearly independent, get rid of some of them. So you have a basis as your column set, and then solve that system instead. So now we're going to assume that A is an m by n matrix and its columns are linearly independent. Consider this example. It's a 3 by 5 matrix. Now, we're assuming that the columns are linearly independent. Each of these columns is a 3 vector. It lives in R3. The dimension of R3 is only 3, and we have 5 vectors, so these can't possibly be linearly independent. So we don't have to worry about this case. We've shown that the number of columns has to be less than or equal to the number of rows. What if it's strictly less than? Let's take this example. This is a 4 by 3 matrix. The input is a 3 vector. The output is a 4 vector. But the dimension of the image is 3 because the image is the vector space spanned by the 3 columns. The dimension of the output space is 4. So not every vector in the output space, in the codomain, is in the image. That means that it's not the case that for every vector B, there's some vector x such that A times x equals B. More generally, given a matrix A that's m by n, define the function that goes from Rn to Rm by f of x equals a times x. The dimension of the image is the number of columns, n. The dimension of the codomain is the number of rows, m. And we're looking at the case where n is less than m. In that case, the function f is not onto. So not every vector b has a corresponding solution x. So we have to lower our standards. Instead of looking for an algorithm that will solve a matrix vector equation ax equals b, given such an equation, we'll look for an algorithm that finds the vector x hat that minimizes the norm of the difference between the target vector b and the vector we get, a times x hat. And the algorithm that we're going to use to solve this is exactly the same algorithm as we used in the case when a was square, although the analysis is somewhat more difficult. Recall the high-dimensional fire engine lemma. It stated that the point in a vector space big V that was closest to a vector b is b parallel, the projection of b onto the space big V. And the distance is the norm of b perpendicular. That is, the projection of b orthogonal to the space big V. Given the matrix vector equation ax equals b, let big V be the column space of A. We need to show that our algorithm will return a vector x hat such that ax hat is as close as possible to b while still lying in the column space of A. That is, that ax hat equals b parallel. Now, let Q be a column orthogonal matrix, such as we get from QR factorization. And let B be a vector. Write B in terms of its parallel and perpendicular parts. B equals B parallel plus B perpendicular, where B parallel is the projection of B onto the column space of Q, and B perpendicular is the projection of B orthogonal to the column space of Q. And let U be the vector that's the coordinate representation of B parallel in terms of the columns of Q. By the linear combinations definition of matrix vector multiplication, the vector we're representing, B parallel, is the matrix Q times the coordinate representation U. Let's take this equation and multiply both sides on the left by Q transpose. We get this equation. Q transpose times B parallel equals Q transpose times Q times U. Now, we know that Q transpose times Q is the identity matrix. So we get that Q transpose times B parallel equals the identity matrix times U. That is, U itself. So we've seen that Q transpose times B parallel is U, the coordinate representation of B parallel in terms of the columns of Q. But now let's look at B perpendicular, the projection of B orthogonal to the columns of Q. For every column, say Qi of the matrix Q, Qi dotted with B perpendicular is 0 because they're orthogonal. Therefore, by the dot product definition of matrix vector multiplication, when we multiply Q transpose times B perpendicular, since the rows of Q transpose are exactly the columns of Q, we get zeros for every row. So we've seen that Q transpose times B perpendicular is the 0 vector. Now let's put these together. Q transpose times B, well, B is the sum of B parallel and B perpendicular. So this is Q transpose times B parallel plus B perpendicular. Now we can use an algebraic property of matrix vector multiplication to rewrite this as Q transpose times B parallel plus Q transpose times B perpendicular. Well, Q transpose times B perpendicular is 0. So we're left with Q transpose times B parallel, which is U, the coordinate representation of B parallel in terms of the columns of U. Now, to go from the coordinate representation u to B parallel itself, we simply multiply by q using the linear combinations definition of matrix vector multiplication. So q times the coordinate representation u is B parallel. So putting these together, q times q transpose times B is B parallel. So here's what we found out. Q times Q transpose times B is B parallel. Now let's use this. We're going to, here's the proposed algorithm for solving the least squares problem. That is, finding the vector x such that ax best approximates the vector b. Here's the algorithm. Find matrices Q and R such that A is the product of Q and R, and Q is a column orthogonal matrix, and R is upper triangular. Then compute C, the product of Q transpose times B, and then solve the matrix vector equation Rx equals C using backward substitution, since R is an upper triangular matrix. Return the solution, which we'll call x hat. We want to show that this algorithm is correct, that it finds the best solution. Well, every vector of the form A times x is a linear combination of the columns of A, and therefore lies in the column space of A. The column space of A equals the column space of Q. Now, by the high-dimensional fire engine lemma, the vector in the column space of A closest to B is B parallel, the projection of B onto the column space of A. The solution x hat given by this algorithm satisfies the equation R times x hat equals Q transpose times B because that's how we got it. We multiply this equation by Q, we get Q times R times x hat equals Q times Q transpose times B. Well, on the left, Q times R is the matrix A, and Q times Q transpose times B is the vector B parallel. So we find that this particular x hat satisfies that A times x hat is B parallel, which is the vector that's closest to B in the span of the columns of A. So we've given one algorithm for solving the least squares problem, where we want to approximate B as A times x. But there are other ways to find such solutions. It's not hard to show that A transpose times A is an invertible matrix in the case where A is a matrix with linearly independent columns, and that the solution to this equation is also the solution that we want. It's exactly the same solution. This is a matrix vector equation with a square and, in fact, invertible matrix. So you can solve this equation using other methods, such as Gaussian elimination. And the equations making up this matrix vector equation are called the normal equations. For a long time, this was the way to find a solution to least squares.